Let's continue our discussion of input data. Next up, growth data. When we design automated systems, especially those that are capital intensive and highly integrated, we must not only look at today's requirements, we also have to look ahead. And that means factoring in projected business growth. Why is this so important? Because automation is not something you implement for a single peak season or for one budget cycle. These systems are designed to operate for 10, 15, or even 20 years. And while they can save considerable costs over time, the savings typically only materialize after a few years of continuous operation. That's why your initial dimensioning has to be based on your expected requirements in the future, not just the current ones. Take a look at the example shown on the slide. It's a bar chart showing Costco's revenue from 2014 to 2025. The revenue almost doubles over that time period. Now imagine if you had designed an automated fulfillment center for Costco in 2014, based solely on that year's volumes. Within just a few years, the system would have been overloaded. Processes would slow down, throughput would drop, and the return on investment would suffer. Admittedly, the Costco example isn't great because Costco has many warehouses. And revenue growth is not the same as growth in material flow. But I think you get the point. So what do we do instead? We design for what we call the design year. This is typically 3 to 5 years in the future. It reflects the business volume and SKU structure that the company expects to reach once the system has ramped up and stabilized. That way, you ensure that the system performs efficiently not only today, but also tomorrow. Of course, forecasting future volumes is difficult, but even rough projections can be helpful. Use historical growth rates, market outlooks, or internal sales targets. Also keep in mind that automation systems are often less flexible than manual operations. You can't just bring in more temporary labor or rent a few more pallet spots when demand spikes. Once the automated system reaches its capacity limit, you hit a wall. Therefore, it's essential to leave headroom in the design, and this headroom must be justified with solid growth data. But also, be cautious of naive extrapolation. Next year, it doesn't have to look like yesterday, just plus 5% orders. If growth expectations your customer provides seem unreasonably high, you should double check with him. If you dimension the system too large in expectation of future growth, the system might become unbearably expensive and provide a big risk to the company should growth expectations not materialize. It can be difficult to design systems that provide a reasonable business case for today's volume. If we add too much capacity for hypothetical growth, the business case will suffer even more. Hence, it is advisable to look for opportunities to expand the same later. Rather than shooting down the project with an over-dimensioned system that's expensive and poses significant risk to the client, you may want to design a system that provides sufficient capacity for the next few years and can be expanded after that. This is easier with some technologies than with others. So if expansion is part of the project plan, you need to choose your technology accordingly to avoid major business interruptions and high project cost later. Next, let's talk about operating hours and, closely related to that, the shift model. At first glance, this might seem like a simple organizational issue, a human resources matter, but it actually has profound implications for automation and system capacity. Here's the basic principle. The more hours your system operates per day, the more throughput you can achieve with the same technical equipment. In other words, by running your system longer, you spread out the workload. That means you don't need as much peak capacity. This does not mean that you should begin to run additional work shifts when you automate. This would defeat the idea of saving cost through automation. But all things equal, an automated system that runs 2 or 3 shifts per day will do better economically than a system that runs only one shift per day. In fact, in many cases, it will be difficult to find a positive business case for automating one-shift operations within an acceptable time frame. In spite of what some salespeople of automation equipment will say, automation has high fixed costs, so the more hours you can run it, the better your ROI. The reason is simple. If you automate a manual system that is run in 2 or 3 shifts, you save labor hours in 2 or 3 shifts. Of course, it would be even better if the system that previously ran in 2 shifts now can be run in only 1 shift because it is so much more efficient. If you can drop night shifts or early morning shifts thanks to efficiency gains, that will of course be helpful for the business case. However, if the manual system already runs only 1 shift per day, it would be hard to justify the investment in automation. Now, assuming that even with automation you have to run the system 2 or 3 shifts, there is an operation benefit to it, workload leveling. If your system can run 24 hours, you can buffer shipping processes, decouple picking from dispatch, and shift work to off-peak hours. This reduces congestion, improves performance, and avoids over-dimensioning. When collecting data from clients or planning your own warehouse, make sure you capture not only the nominal shift times, but also the actual productive time. Breaks, downtimes, and changeover times matter. Let's now move on to the next key data input, order data. Order data is perhaps the most central and valuable data source when it comes to designing and optimizing intralogistic systems. It is from this data that we derive how goods move through the warehouse. Order data gives us insight into how many orders are processed, how big they are, how many lines each order has, and how they are structured across time and customers. Let's begin with the basics. The table shown on the slide lists some real or simulated order data, including an order number, date and time of pick, the item number picked, pick quantity, pick unit like piece, case, pallet, and the customer. To make things more intuitive, look at the little sketch above the table. My shopping list. Imagine you go shopping and your list has 3 items, 1 pack of coffee, 4 avocados, and 2 kilograms of potatoes. That's 1 order, but 3 order lines. And one of these lines has a quantity of 4 avocados. This illustrates how order data breaks down. 1 order equals 1 complete purchase transaction. 1 order line equals 1 item in the shopping list. Quantity equals how many pieces or units of that item were picked. Why is this distinction so important? Because it affects every single element of warehouse planning. This is one aspect of system design we will discuss in great detail. Also, not all pick units are equal. Picking 1 pallet takes a forklift and time. Picking 1 piece by hand takes a few seconds. The distinction between cases, pieces, and pallets is essential for designing ergonomic and efficient systems. The left side of the slide shows a data table. This is what you might receive from an ERP or WMS export. The right-hand side lists and explains the fields we typically need for analysis. Let's go through some key fields. Order number. This is the unique ID of each order. It could be a purely numerical code or an alphanumeric string. Without this field, we can't group lines together into a complete order. Item number. Again, this is a unique ID, but this time for the product. It allows us to join with master data, to retrieve dimensions or categories, and perform various analyses. Date. This can mean different things depending on the use case. Is it the date the order was placed, the date it was picked, shipped? Ideally, we want to have separate fields for pick date, ship date, and order date to track process times and system loads accurately. Time. In high-frequency environments, timestamps matter. For example, in fast-moving warehouses, knowing that 3 orders were placed at 9:02 and another 5 at 9:07 helps us understand order spikes. When paired with data on actual pick start time and duration, we can analyze bottlenecks and operator performance. Quantity. This seems obvious, but don't forget that the number alone is not enough. We need to know what unit that quantity refers to. Is it pieces, kilograms, cases? Pick unit. This field tells us exactly what unit the item was picked in. As mentioned earlier, this is essential for understanding the physical process. Some additional optional fields that are often important. Customer number, especially useful in B2B environments where different customers may have different profiles. Order size, frequency, priority. Shipping load number. If available, this helps group orders into shipments, which is useful for outbound consolidation and truck planning. And here's a very important reminder. Order time is not the same as picking start time. Don't confuse the two. Orders might be placed at 11 p.m., but only picked the next morning. Without clear timestamps, your analysis can misrepresent reality, especially if you're calculating lead times or peak loads. Many orders might be placed on the weekend, but only be processed on Monday morning. I will show you an example of this later. Poor data quality or missing fields can drastically reduce the accuracy of your design. So when you receive order data, don't just import it. Inspect it. Understand it. And always verify. Is this the full picture?